Okay, so now let's discuss, do a problem about a fast exponentiation algorithm. So that's a fast modular exponentiation, and the idea of the algorithm is just repeated squaring. There's another name for this algorithm. So let's take an example here to explain what to do. So let's take, okay, before the example, let's try to explain why this is a shorter algorithm than the usual brute force approach. So let's see, for the sake of the argument, we want to calculate a to the power 100. So let's see how many multiplications we have to do. So just entering a, let's say it counts as one multiplication. So starting from 1, which means nothing, the blank slate, we get an a. So that's the first multiplication. Then we get an a squared multiplied by a at every step, multiplied by a at every step, get a cubed, and so on, multiplied by a, get a to the power 4, and so on, and so on, and so on, and so on, multiplied by, so we get a to the power 99 at some moment, multiplied by a, we get a to the power 100. So how many steps we cover here? Multiplied by a, from a to the power 1 to ending to a to the power 100, we got 100 multiplications. 100 multiplications with brute force. What about the extended, the idea of between fast exponentiation or repeated squaring? Repeated squaring is the fast version. Okay, so let's start with a. Then at every step, we just still a multiplication, but we just square the previous input. So squared, we get a squared. Squared, we get a to the power 4. Squared, we get a to the power 8. One more time, we get a to the power 16. One more time, a to the power 32. The objective is to calculate the 100 power, so we don't want to go past 100. So one more time, square it. If you square a to the power 32, we get a to the power 64. Okay, so how many multiplications is this so far? 1, 2, 3, 4, 5, 6 multiplications. Okay, so let's see. What now? At this moment, let's try to. We need a to the power 100. So let's make a try to combine those exponents, which are powers of 2, from 1 is to the power 0 to the power 64 is to the power 6. Let's combine those exponents to get a 100. We can do like think about a greedy algorithm. So out of 100, try to get 100. Out of those exponents, grab the biggest amount, biggest power of 2 you can. So 64. What's left? It's 36. How much can I grab out of 36? 32, right? And what's left is 96. Is 4. It means I just already grabbed 64 and 32. I got 96. So what do you get here? Basically, you can a to the power 100 equals to a to the power 64 times a to the power 32 times a to the power 4, right? Because 100 is 64 plus 32 plus 4 is 100. So a to the power 100 is the exponential of the sum is the product of the exponentials. So how many more multiplications we do? We multiply these two, get a result, and this result we can multiply with this one, we get 2 more multiplications. So overall, the fast repeated squaring method calculates a to the power 100 much faster with 8 multiplications. So that's the idea, in an informal way. Let's try to apply it concretely on a concrete case. So let's see. So let's calculate. The example is 417 to the power 315 modulo 931. So this will be a calculation in the residue class ring Z sub 931. The calculation in Z sub 931. Now, the difference from the type of table in the extended Euclidean algorithm is now this table has only two columns. So let's do step one of the algorithm. Repeat it square. Do the table. K versus 417 to the power K modulo 931. So never forget that all we care is remainder modulo 931. Okay, so let's see. A couple of rows here. Okay, let's see what we get. Let's initialize data entry. If k equals to 1, 417 to the power 1 is just 417. So that's the data entry. You just enter the data. Now, how to advance in the algorithm? We advance differently in the left column and the right column. In the left column, always at every step we double. In the right column, we square. Square modulo 931 every step. Okay, so double it, 2. And then here we multiply 417 times 417. That's a big number. This 417 squared, we divide by 931. We only care about the remainder. So 417 squared, I did this calculation for you. Just double check everything which we do here is 723. Okay. Repeat. There's idea of algorithm. Double, so we get a 4. Now got this number 723, big number, square it becomes bigger. This big number divided by 931, and only the remainder matters for us. So we get 438. Double. 430 squared is 58. Double. 58 squared is 571. Like I said, verify everything we do here. Double, 32. 571 squared is 191. Double, 64. 191 squared is 172. Double. So how far do we go? So the objective is to calculate 315 power. So with a power of 2, so everything is a power of 2. We don't want to go past 256. So let's see. 128. Square 172. Get a big number. That big number again divide by 931. We only care about the remainder. So 172 squared is 723. It just happened that this we got a cycle here, so the 128th power is the same as the second power, which means if we do 256, we'll get 438 again. Okay, that's the first step of the algorithm. Step 2. Step 2 is a greedy algorithm. We have to basically writing down 315 in base 2, but you can reformulate it as a greedy algorithm in expressing 315 as a sum of items in the first column. So let's see, 315 equals, grab the biggest item in this column that you can, that's greedy. So it's 256 plus, what's left is 59, right? Put 59 here, the what's left under the plus sign, just to keep track of this. So 256 plus 59. Okay, now, Grab the biggest power of 2 out of 59. We'll get 32. What's left is 27. Grab the biggest power of 2 out of 27 is 16. What's left is 11. And also, the line is clear. 11 is 8 plus 2 plus 1. Plus 8 plus 2 plus 1. So, this concludes the step 2 of the algorithm, which is the same with writing 315 in base 2. We just we use this greedy algorithm to represent 315 as a sum of items in this column. Step 3, let me put it here. Step 3, 417 to the power 315 equals to 417 to the power 315 is the sum of those items. So 417 to the power 256 plus 32 plus 16 plus 8 plus 2 plus 1. So again, exponential of the sum is the product of the exponentials. Is 417 to the power 256 is 438 times 417 to the power 32 is times 191. 438 times 191 times the 16th power times 571. The 8th power times 58. The second power, 723. The first power is 417. So 438 times 191 times 571 times 58 times 723 times 417. So yes, we do this calculation. So we could do, if we're like a 3, we can do this 2 with this 2 with this 2, and then we can do like this. But anyway, the result after all of this work comes out to be 246. So, how to write down the conclusion? So the conclusion is after this fast exponentiation algorithm, let's see how many multiplications we did here. So we just let's say that let's give the total select, so we get a just entering this number counts as one multiplication. So 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications. Then well, writing in base 2, let's say it doesn't use any multiplication. Then for this one, 1 multiplication, 2 multiplication, 3 multiplication, 4, 5 multiplications. So 5 plus 9 is 40 multiplication. 40 multiplications to calculate the 315 power. Right? So which is again reflects the effectiveness of the fast exponentiation algorithm. Okay, so let's discuss a special example of powers in modular arithmetic. A very special power in Zn. So Zm is the set of, again, like always, Zm is the set of all integers modulo m. So 0, 1, 2, up to m minus 1, which are all possible remainders that we can get when dividing by m. Okay, so let's use the following theorem. We already discussed about it. A belonging to Zm is invertible equivalent by definition. There is a B in Zm. Okay, here's the definition first. Let me do the theorem. So definition, A belonging to Zm is invertible equivalent by definition. There is a B in Zm such that A times B equals to 1 in Zn. And now comes the theorem. The following are equivalent. First, A belonging to Zn is invertible. And second, greatest common divisor of A of M equals to 1. So to be invertible means to have no common factors with M. So invertible equivalent, no common factors with the modulus. Okay, so we discussed about this. Prior to that, we discussed about like inverses in for the method of fine encryption. For example, 11 inverse equals to 19 in Z26. Because 11 times 19 equals to 209. And if we divide 209 by 26, what's the biggest multiple of 26, which is less than 209, is 208. So this will be 208 plus 1, but the 0 on the account that is divided by 26, so this will be 1. So 11, 19 are inverse to each other in the ring Z26. To be invertible means, again, to be invertible is no common factor with the modulus. Now, the most, like we discussed about we announced a very special power law. Let's give it. That's Euler's theorem. So let's discuss about Euler's theorem. Very special power law, Euler's theorem. So let's say phi of m, let's define phi of m, the Euler's torsion function is the number of invertible elements in Zn. Then, if A belonging to Zn is invertible, we have A to the power phi of m equals to 1 in Zn. Or congruent to 1 mod m, we can say. Okay, so how let's try to give a proof of this. So let's denote the set of invertible elements in Zn by U of Zm, as in units of the ring Zm. So so say U of Zm consists of x1, x2, all the way through x sub phi of m. So let's list all the invertible elements in Zm. We know there are phi of m of them because that's how we define phi of m, the number of invertible elements in Zm. Okay, and then let A be one of them. So let A be an element of U of Zm. So in other words, that is A is one of those. So that is A is one of those. One of those. Okay, so given that A is one of those, let's try to consider the products AX1, AX2, AX3 up to A times X sub phi of m. The multiplication is in the ring Cf. So consider the numbers AX1, AX2, all the way through A times X sub phi of m. Okay, so first of all, they are distinct. So first of all, important. So important fact: ax1 through ax sub phi of n are distinct. Let's see. Let's call this fact number 1. Fact number 2: ax1, ax2, all the way through ax phi of n are, all of them are in u of zn. Okay, let's try to take a moment to prove those things. So let's continue. Continue to prove. So we now have fact 1, so let's prove fact 1. How to prove that ax1 through ax phi of n are distinct? Okay, let's assume by contradiction, say axi equals to axj, but in z sub n. Okay, now we know that a belongs to u of zn. That means invertible. So multiply this relation with the inverse of a. So we get a inverse times axi equals to a inverse times axj on the account that axi equals to axj. So axi equals to axj, multiply both terms to the left by a inverse. To the left or to the right doesn't matter because everything is commutative here, but still is more visible. So in this case, it means xi equals to xj, right? And that's a contradiction because if axi equals to axj, we assume that I is not j, right? But then we get a contradiction in that xi turns out to be equals to xj, and from the beginning we assume that u of zn is listed at x1, x2, all the way through x sub phi of n. So different subscripts means different elements, and these are all elements invertible in Zn, the units of Zn. So x1, x2, x phi of m are distinct. That's the proof of fact 1. Proof of fact 2 is again is even easier. So fact 2, A is one of them. So one of those numbers, x1, x2, x phi of m. So A is invertible. Xi is invertible. So A is invertible. Xi is invertible. Therefore, Axi is also invertible. And the inverse of this product is the product of the inverses, because everything is commutative here. So we just proved fact 1 and fact 2. So in other words, so let's put everything together. We got u of zn equals to x1, x2 through x sub phi of n. And then by using fact 1 and fact 2, the same u of zn can be listed in a different way as ax1 through ax2 through a times x sub phi of n. So this list is the same with this list, only it's just a permutation of the list number 2 is a permutation of the list number 1. Right? So if the second list here is the same as the first list, only that the numbers are shuffled, the product of the items in the first list must equal the product of the items in the second list. So what's the product of items in the first list? It's x1 times x2 times x3 all the way times x sub phi of n. What's the product of numbers in the second list? Again, the second list is the same as the first list, only reshuffled. The product of numbers in the second list is a appears how many times? Phi of n times. So it will be a to the power phi of n. Again, times x1, x2, x3 all the way x sub p of n. What we got here? Product of all invertible elements. Product of all invertible elements. Let's call this capital X. Capital X is the product of all invertible elements. By definition, since we know the product of two invertibles is invertible, X is invertible. So we got X equals to a to the power phi of n times X. Then, because X is invertible, because it's product of invertibles, that means multiply both sides by X inverse, 1 equals to a to the power phi of n in Zn. Or a to the power phi of n, if you want to write use congruence, is congruent to 1 modulo n. That's Euler's theorem. Or a to the power phi of n equals to 1 in Zn is that even better from the point of view of algebra. Okay, so let's give a concrete example just to gain more trust into this. Okay, so let's see. And in this example, let's again use the fast exponentiation algorithm. And that's one example by hand. Let's see what I got here. Say n equals to 77. So the formula for phi of n, so if n equals to p1, we'll prove it right after. Let me prove it right after we finish this example. If n equals to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, let's say this is a prime factorization of m, then phi of n equals to n times 1 minus 1 over p1 times 1 minus 1 over p2 all the way to 1 minus 1 over pk. So in this case, if m equals to 77, which is what's the prime factorization of 77 is 7 times 11. Then phi of 77 equals to 7 times 11 times 1 minus 1 over 7 times 1 minus 1 over 11 equals to 7 times 11 times 6 over 7 times 10 over 11, 7, 11 with 11, we get 60. In general, we can do phi of a product of 2 primes pq equals to p minus 1 times q minus 1. It's a very quick, useful to keep it in mind. Okay, so let's go back to this example. So phi of 77 is 60. So let's pick up a number which is no common factor with 77. What's the smallest size number? Let's except 1. So let's make it 2. So what does it mean Euler theorem? Euler theorem translates into what in this special case? 2 to the power Euler theorem is 60 equals to 1 in Z77. So let's check it. Let's go back to the table from the fast exponentiation algorithm. K versus 2 to the power K mod 77. And a couple of lines here. We'll see. 1, 2, so where should we stop? 4, 8, 16. So we got the power 60, right? 32. That's it. We don't want to go past 60. To the power 1 is 2. To the power 2 is 4. We just square this one, so 4. To the power 4 is 16. To the power 16 is 256. Let me give you the result. You verify everything. We'll get 25. 25 squared modulo 77, it would be a 9. And 9 squared will be, well, 81 modulo 77 is a 4. This we can do without calculator. Okay, and then step 1 of the algorithm. So now let's express step 2. 60 as the sum of exponents in this line is 32. What's left? 28. So we got a 16. So far we got a 48 plus 8 plus 4. That's step 2. And then to the power 60, therefore is to the power 32 times to the power 16 times to the power 8 times to the power 4. And from the table, this will be 4 times 9 times 25 times 16. Let's do it by hand. So let's see what's the quickest way here. 9 times, let's take this 2. 9 times 25 is 225. What's the closest multiple of 77, which is close by? The multiple of 77 is close by. 3 times 77 is 231. So 231 is a 0 in Z77. Let's go back from 0 back 6 units to 225. So this will be minus 6 in Z sub 77. What about the other two? 4 times 16 is 64. 64. Now 77 is a 0. So to get from 0 to 64 it will be minus 13. 6 times 13, minus 6 times minus 13 is 78. Right? So minus 6 times minus 13 is 78 because appears a plus. But 78 more 77 is the same as 1. So we just verify the Euler's theorem in that for this invertible element in Z77, the phi of 77th power of the invertible element is 1, which kind of is a verification in this special case for Euler's theorem. Okay, so one more thing. So I just let's give a very intuitive reason, heuristic reason why phi of m, if m equals to p1 the power alpha 1, p2 the power alpha 2, all the way through pk the power alpha k. So in other words, if p1, p2 through pk are the prime factors that go into m, why phi of m equals to m times 1 minus 1 over p1 times 1 minus 1 over p2 all the way to 1 minus 1 over pk. Okay, so look at the numbers 1, 2, 3, all the way up to n. So pick up a random element in this set. So pick up a random element in here between 1, 2, up to n. Okay, so what's the probability of A being a multiple of P1? Probability of A being a multiple of P1. Well, it's 1 over P1 because 1 out of every P1 numbers in this list is a multiple of P1. So it's 1 over P1. Okay, now what about the opposite event? So probability of A not being a multiple of P1 is 1 minus 1 over P1. Right? But we want to how to count intuitively elements in between 1 and m, which are no common factors with m. That means elements between 1 and m, which are not multiples of P1, and not multiples of P2, and not multiples of P3, all the way through not multiples of Pk. So we have to that's a heuristic argument. We need more. I mean, to make it formal, we need more, but still to get a quick, ascertainment of the statement through a heuristic argument is probability of a random element between 1 and m to be relatively prime with m is the product of those probabilities, not being a multiple of P1 and not being a multiple of P2, and all the way through not being a multiple of Pk. So the probability of A being relatively prime with M is 1 minus 1 over P1, not a multiple of P1, times 1 minus 1 over P2, and not a multiple of P2. And all the way through 1 minus 1 over Pk, so, and lastly, not a multiple of Pk. So probability of a random element in this list not being relatively prime with M, in other words, being invertible modulo M, is this. Therefore, the number of invertible elements is the number of elements in the list multiplied by the probability of an element being invertible. So therefore, phi of M equals to M times 1 minus 1 over P1, 1 minus 1 over P2, 1 minus 1 over Pk. The most special case of this formula is the Euler phi function for RSA numbers, which will be phi of p times q. A product of 2 prime is p times q times 1 minus 1 over p times 1 minus 1 over q, like we discussed before for 77. So this will be, let's couple this p with the first parenthesis and the q with the second parenthesis, and we'll get p minus 1 for the first coupling and q minus 1 for the second coupling. So this will be the Euler phi function of an RSA number.